I posted the link to Troll Game in the chat, so you can just click on that link. You might need to sign up for the contest, so just log onto your HackerRank and you can sign up for it, and it'll allow you to see the problem. And you can code a solution to it also.
We can see the problems without signing in, but
Oh, okay.
Sign in
Yeah.
box.
Also, Ishan, you were talking on mute.
Okay, so in this problem troll game, you're playing a game with your friend, and if a level has a troll in it, then that's marked with a 1. If a level does not have a troll, it's marked with a 0. So your friend starts off by playing the first game, and after that, you guys can take turns. He can play however long he wants, you can play however long you want, and you guys can alternate, or he can play the whole game, whatever. But he has to play the first level. So the question is asking you to output the minimum number of levels that you and your friend can lose. And whenever there's a troll, whenever there's a level of the troll, your friend will lose. So in this example, you can see the friend starts off playing this level, the first level. The first level has a troll, he's going to lose. And the minimum number of levels that you and your friend can lose when you play the whole game is 1 for this example.
Yeah,
Does
and just
anybody see
note
the
that like when you play, you can never lose to a troll, but only your
Yeah.
friend will.
Yeah, you can never lose to a troll, only your friend loses, and that's when it's a 1. So does anybody want to take a stab at the solution? The solution is actually really simple, and it's also really short. You just print out this number over here. Because the strategy is your friend plays the first game and you play the rest. Your friend plays the first level and you play the rest of the levels. So the answer is just whatever this number is over here. So if this had
That
been
would be
all
because
ones, then your friend plays the first level, you play the remaining levels. And yeah, then the answer is 1. If this had been a 0, then the answer is 0 because your friend plays the first level. Since it's a 0, he does not lose, and you just play the remaining levels. So that was troll game, and it's also a troll problem. That's why I gave it that name. Yeah, and if you want to take a look at the code, it's really short. Let's see, where is it? Troll game here. It's pretty much 3 lines if you exclude like the imports and main stuff. Just create a scanner, read in the n, and then read in the next number and print that out. So that's the solution for troll game. The next one we'll go over is elves 1, which Madhu will explain, but first you guys can go ahead and read the problem. And I'll post the link in the chat. Madhu, did you want to share your screen for this part?
No, it's fine. I can just
Okay.
be verbal with it.
Yep. So I think hopefully that was enough time to get a gist of what the problem's asking. And Madhu, you want to go ahead and explain it?
Yeah. If you guys just need more time, you can say it. Otherwise, I'm just gonna start explaining this. So you're given one number, which tells you like how many presents there should be for each present type. And then the second number in the first line is the number of presents you need to read in. So if you look at the sample input 0, you can see that we have car, mug, color book, mug, car. So there's 2 cars, there's 2 mugs, but there's only 1 color book. So because there's only 1 color book and not 2, which was specified in the very first number of the input, that's what we're gonna print out. And just note that like if there were multiple presents that are only like one of them, so like, let's say we had like a color book and we had like headphones, we would have to print out color book then headphones because it wants us to print it out in alphabetical order for the output. And you can pretty much do this problem by using a map. So the reason a map is effective is because you can have a key be your key. The key of the map can be like whatever name of the present is, and then the value for that key can be the amount of instances of that present. And then what you would do is you just read each present, and if it's already in the map, you would just take the value and increase it by 1. Otherwise, you would create a new key with whatever name that present is. For example, car, and we would give it a value of 1 because it's not already in there. So after you read in all the data, you might need to sort them in alphabetical order, unless you're using like a tree map, which I'm pretty sure is already sorted for you. But I know if you're using a hash map, you might need to sort in alphabetical order. And then when you go through the list of presents in your map, you need to check if the value associated with each present is not equal to the number of presents there should be. And that's, remember, the very first number in the problem, which is like the number 2 in this instance for sample input 0. If the value is not equal to 2, like the value of that key, then you would need to print out that present type. So that's pretty much a solution
Okay.
for elves. Ishan, you can show the code for it.
Yep, just a second. Don't know what's happening. Okay, yeah, so this is the code, right?
Oh wait, no, that's not the code. 1 second, I can just send it to you because that's.
Is it presents.java?
Yeah.
Okay. Yes, you
Yeah,
can
that's
see
pretty
it's
much the
using a
code.
map, and then there's the keys, the string, the values, and integer, and then it reads in the input, puts into the string, puts into the map, and increases its count. And then if it's not equal to, if the quantity of a item is not equal to the requested amount, it's going to print out that item.
Yeah, and if on line 14, what getter default means is like it will try to retrieve that value from a map, and if it doesn't find that key value, like let's say can't find the word cookies, it's gonna, well, pretty much what's gonna happen is that it's gonna create cookies and then put a default value of 1. Otherwise, if there's cookies, it's gonna retrieve the value and add 1 to it. So that's what's going on in line 14.
Yep, and the next problem is minimize difference. So we'll take a look at that. You guys can go ahead and read it, and then we'll discuss the solution for that one. Okay, so this was a shorter problem. It has a short problem statement. So I'm just going to go ahead and explain it now. And if you need more time, you can just let us know. So basically, you're given an array of integers like over here, and you need to find a value of x so that this amount described over here is as small as possible. So I'm going to go ahead and do this on a whiteboard so it's easier to understand. Just a second. Okay, you guys can see the whiteboard now, right?
Yeah.
So we have these 6 integers, 1, 2, 3, 8, 11, and 14. And we need to find some integer x so that like x minus the difference between x and 1, the difference between x and 2, the difference between x and 3, and all of these numbers, when we add up those differences, we want them to be as small as possible. And I'm just going to go ahead and right now and say that the answer is 8. And now we're going to take a look at why the answer is 8 and how the solution works. So the solution for this problem is to take the biggest median, is to take the median of the numbers over here. And if there's an even number of integers, as in this case, there's 6 integers, the answer for x, it's going to be the the bigger number that's in the middle, which is in this case is 8. So let's say x is 8. X is our answer. That's the thing we're subtracting from all the numbers. And we have our distances to all the other numbers. So 8 minus 3 has a difference of 5. 8 minus 2 has a difference of 6. 8 and 1 has a difference of 7. 8 and 11 is 3, and 8 and 14 is 6. Now, what happens if I take this x from 8 and I shift it over to 7? Think about what happens. What happens to the 5? What happens to the difference between 3 and x now? It goes from 5 to, what's 7 minus 3?
4.
Yeah. So if we, instead of making x 8, if we made x 7, this becomes 4. So that's minus 1. And the 6 over here is also going to decrease by 1. And the 7 is also going to decrease by 1. Because we just took x and moved it closer to all the numbers on the left. We just moved it closer to these. But at the same time, while we moved it closer to the 3, 2, and 1, which is a good thing, we moved it farther away from all the stuff on the right. We moved it farther away from 14. So now instead of being 6, the difference between x, which is 7, and 14 is going to be 7. The difference between x and 11 is going to be 4, not 3. And the difference between x and 8 is going to be 1. So by shifting the x over to the left, we increased the distance to the numbers on the right, and we minimized the distance to the numbers on the left. And that's why if you choose the median, which is in the middle of the numbers on the right and the numbers on the left, you're going to have the minimum possible sum of like 7 plus 6 plus 4 of all these differences. So that's the solution for minimized difference. It may take some playing around with to understand fully, but that was pretty much the solution. And once again, it was a short solution. You just read in an array, sort the numbers, and you print out the median. So that's the end of the basic problems. Now we're going to be moving on over to some more fun problems that use some algorithms and stuff. So the first of those problems is building blocks. And this is what we'd call a greedy problem. So go ahead and read this problem, and we'll discuss how to solve it. If you need any more time to read the problem, you can just let us know in the chat. The gist of this problem is that you have a bunch of blocks, you're given their widths and heights, and you need to stack them. And there are two things you have to find. You have to find the minimum number of stacks that can be built using the blocks and the maximum possible height of a stack. So the catch is you can't just keep on stacking blocks on top of each other. If you put a block on top of another block, it has to have a smaller base than the block below it. So if you have a box that's really wide, you can't put it on top of a box that's really narrow. You have to put the narrow box on top of the wide box. So that's how this problem works. And you define these two things, the minimum number of stacks that can be built and the maximum possible height of a stack. So we're going to take a look at an example of that. Over here we have these are the widths of the blocks: 2, 14, 2, 10, and 14, and these are the heights. We're going to ignore the heights for just now and focus on the widths. So with these widths, we have two blocks with a width of 14. We have two blocks with a width of, we have one block with a width of 10, and we have two blocks of a width of 2. So that's what these numbers over here tell us. These are what the blocks look like. We're just going to ignore the heights for now. So now we are to try to figure out the minimum number of stacks that we can build with these blocks. So for example, one stack may look like a 10 with a 2 on top. Another stack may look like the 14 with a 2 on top. And then we may have just a 14 by itself. And that's 3 stacks. We have to use all the blocks, and we created 3 stacks with these blocks. But we want to find the minimum number of stacks that we can possibly make. So are there any ideas for how we could possibly do this? Any guesses are welcome.
You talking about for the minimum number of stacks?
Yeah.
I would probably guess that it would be the maximum number of duplicates would be the minimum number of stacks.
Yep, that's the answer. That's correct. So what Matthew said is the answer for this problem is the maximum, the block with the maximum frequency, the block width with the maximum frequency. So for in this example, we have 2 blocks of width 14. So 2 14s, we have 1 10 and 2 2s. The answer in this case is going to be 2. And the reason for that is because we can take the 14, we can put a 10 on top, we can put a 2 on top. No, well, actually, I'm going to explain this a different way. Let's say we had 1,000,000 blocks of size 1, of size 100, and maybe 10 blocks of size 1. Even though we only have 10 blocks of size 1, we have 1,000,000 blocks of size 1,000,000. We have a really large number of a million blocks. And because we cannot stack blocks on top of each other unless the block on top is smaller, each of those 1,000,000 blocks is going to have to be on its own stack. So in this example, with the 2 14s that we have, we know for a fact, because 14 is not less than 14, each of these blocks over here has to get its own stack. So this is going to be 14, this is going to be 14. We know that 10s are going to get its own stack, so we can put a 10 here. We know that 2s are going to get their own stack, so we can do something like this. If I instead had 4 14s, each of those 14s would have to have their own stack because they can't be put on top of each other. And so that's why the minimum number of stacks is simply the largest frequency of a block width. And now for the maximum possible height of a stack, are there any ideas for how we can achieve that? So now the heights over here do matter. It's like this block over here has a height of 9. This block has a height of 5. This block has a height of 5. This is 6, and this is 10.
I'm thinking
Think about
that,
this.
you could sort you can sort the numbers, and then like you would actually, I mean, I think going through the list of numbers would be inefficient, but I was just thinking you could like go through a list of numbers, and if there's like no duplicates, you would add 1 to your final counter and then like just print it out. That's what I'm thinking. But it seems inefficient because you have to go through an entire array again.
I'm just going to draw the answer to this problem so it's easier to visualize. So this is a height of 10. This is 5. And then this is really tall. This is 9. So the answer for this case is 24. We can take this block over here, this block, and this block. Okay, so I'll go ahead and explain the solution. The solution for getting the maximum height, we want to be greedy about this. And this is where the greedy part of the problem comes in. A greedy problem is basically one in where you take the choice that looks the best in your current position without worrying about steps in the future. And typically they involve sorting. This one does not involve sorting. So this problem is greedy because we're going to take for each block width that we have, so we have block widths of 14, 2, and 10. We're going to take the block with the biggest height. So for blocks of width 14, what is the biggest height that we have for blocks of width 14?
It looks like there's a 10.
Yep, 10 is the biggest. Okay, for blocks of width 10, what is the biggest height that we have?
Maybe the only one in existence.
Yeah, 5. And then for blocks of width 2, the biggest height that we have is 9. So we're going to be greedy about this, and the solution is just to, for each block width, take the maximum height block. And the reason for this is because these blocks have different widths, we're taking only one thing from the 14 stack, we're only taking one from the 10 group, and we're only taking one from the 2 group. We can stack these blocks on top of each other. So we can have something like a width of 14, a width of 10, and then a width of 2. The thing that we're trying to maximize is their height, and that's why we take the maximum height from each group. So that's a solution for what's it called, building blocks. And this solution also used a hash map. So I'll just quickly show the code so you guys can get a better understanding of what the solution looks like. Okay, so this is it over here. Where is it? Building blocks. Here it is. So you can see I'm using a tree map. You can use a map as well, a regular hash map. I have one hash map for the frequency, and this will store the number of times that a certain block width occurs. So for example, we had 2 blocks of width 14, 2 blocks of width 2, and 1 block of width 10. This one stores the maximum height for each block width. So for example, for 14, the maximum height was 10. For 10, the maximum height was 5. And for 2, the maximum height was 9. This loop over here computes the minimum number of stacks. This loop over here computes the maximum height, and it just prints it out. That's the solution for building blocks. And now we're going to take a look at another problem called video games, which Madhu is going to cover. So this is linked to the video games problem. Okay, I think that's enough time to read the problem.
Okay. So for this problem, you notice how all the input follows the same format where you're given the name of the video game, the time played, and a rating. You can kind of make an object class out of that where your instance variables might be like the name of the video game, the time played for the video game, and the rating. And note that we would have to sort by multiple different fields because you would have to sort in the order of minutes played, the time played, rating second, and then the title third. So just using like a collection sort isn't immediately going to work because you would have to compare with multiple instance variables. And if we just created a compare to method, a compare to method would only compare like one of the instance fields. So it's not exactly the most effective thing you can do. So for this problem, if you go to videogame.java, yeah, that would be your object class. You just have your 3 instance variables, and then you would just return you would just have your getter methods, which just return the instance variables. and then you have your constructor where you can construct a video game. So if we need to use comparator because comparator allows us to compare using multiple instance fields. And by using comparator, it makes this problem a lot more easier. So if you go to rating compare, yeah, so I use comparator here. So first I'm comparing in the order that the problem wants it in, where I have time played first, then I have the rating, and then I compare by the name last. So for exactly what you want to return, like returning -1 or 1, you would kind of have to play around with it. And like eventually you get used to knowing if you want to return 1 versus -1. And then at the very end, on line 13, I returned 0 because if none of the above are true, what it's saying is that they're the same exact video game with the same time, the same rating, the same name also, and yeah. So you would just compare the video games through their instance variables. And then in your main class, yeah, you would just read the input, which is what the first 20 lines are about. And then lines 20 through 27, it's the line 20 and 21 is using the rating compare class, like the comparator, which will automatically sort all the video games based upon whatever we wrote in the rating compare class. And on line 22 through 27, we're just printing up the video games because it'll be in order by then.
And if you need a refresher of comparators, this is something Madhu and Kanish covered in our previous lesson. Part of the tutorial, part of the meeting was on YouTube, so you can check that out. And then it's also on our GitHub. So if you want to take a look at the code for that. Are there any questions about any of the problems so far?
All right, I just want to add one thing about this. So in this problem, we used the main class and 2 other classes. But you might be wondering, oh, here we have 3 files. We can only submit 1 file to HackerRank. So if you wanted to have those 2 other classes in the same file, you would have to declare them like not public. Instead, just declare class video game. And if you do that, it'll be fine.
Yep.
So like if a class is public, that means the class's name must match with the file name. But if it's not, then it's fine. So yeah, that's just a heads up for those.
Yeah. Okay, the next one will be wall painters. So here's a link for wall painters. And if you've done math counts, this problem should be, maybe it would be familiar for you. Okay, so this is pretty much the problem statement. So I'm assuming everybody's done, and I'll be explaining the problem anyways. So in this problem, you have a bunch of people who are working together to paint walls. This is the number of people, this is the number of walls, and you're given how long each of them takes to paint a wall by themselves. So for example, this first person takes 2 hours to paint 1 wall, working by themselves. So if they have to paint 4 walls, it's going to take them 8 hours. But in this problem, these people over here, these 3 people, they're working together to paint the 4 walls. And you have to print out the minimum number of hours accurate to 3 decimal places that it will take them to finish painting those walls. So in this case, the answer is 4, because after 4 hours, how many walls has this first person painted? They take 2 hours to do one wall, and they had 4 hours of time. So how many walls did they paint? You guys can type into the chat or unmute yourselves.
First guy's done 2, second's done 1, third's done 1.
Yeah, that's correct. It's just division. So if they have 4 hours to paint the walls, this person has done 2, because 4 divided by 2 is 2. This person takes 4 hours to paint one wall, which means in 4 hours they've done one wall. This person has also done one wall. So after 4 hours, they've painted a total of 4 walls. And that's why 4.000 is the answer. But the thing is, this is just a simple case. You may have 1 million people painting a wall, painting the walls. And you may have as many as 100 million walls to paint. So this is where it gets a little more complex. But the idea behind the problem stays the same. And if you didn't catch them, there's a mathematical solution to this problem. And there's also one that uses a binary search. Remember, we covered binary search last semester, and the video's up on YouTube, so you guys can check that out. We covered binary search in 2 separate sessions, I think. So I'm going to go ahead and share the whiteboard now, because we're going to be doing some drawing. Okay. So let's say we have this person over here who takes 2 hours to paint a wall by themselves. And let's say we give them T hours to paint a wall. My question to you is, how many walls has this person painted after T hours? Can you come up with an expression for that? They take 2 hours to paint one wall by themselves, and we give them T hours to paint walls. So how many walls have they painted? Yep, once again, just division, because we give them T hours, they take 2 hours to do one wall. So they take T, if we give them T hours, this tells us how many walls they have painted. Now let's make this a little more complex. Let's say we have a second person over here who takes 3 hours to paint a wall by themselves. How many walls has this person, this guy over here, just this guy, how many walls has he painted after T hours?
What if it was just T divided by 3? Wow, magic.
Yep, it is T divided by 3. So we can see that, let's say our answer is T. T is how long it takes to paint how many of our walls the problem statement gave us. It's going to
Why did that T look like an A?
Huh?
Why does that T look so much like an A or a stick figure guy?
Yeah, that is true. It's kind of hard to draw on here, but let's just pretend that's T. So the total number of walls that are painted by both the people after T hours is going to be T over 2 plus T over 3. Because this is how much the first person has painted, this is how much the second person has painted. And let's say we want to find how much time it takes them to paint 5 walls. So we want to find what T equals when this expression is 5. So now you can see that to solve this equation, one thing that we can do is if we divide both sides by T, we get 1 over T plus 1 over 3 equals 5 divided by T. So what we can end up doing is dividing, and then actually let's go further and let's try to solve for what T equals. So we have this equation. I'm not sure if I can zoom out a bit. So we have this equation over here. Let's try to get T isolated by itself. So what we can do is we can multiply by, well, actually, let me think about this. How do I want to explain it?
So you want to test for different values of T, right?
Yeah. So what we can do is we can calculate what this equals by using the for loop. So let's say we have n people, we can calculate what this equals. Once we find out what this equals, we're going to take that and divide it into the 5. And that gives us the value of T. Because T is equal to 5. If we solve for T over here in this equation, T is equal to 5 divided by 1 over 2 plus 1 over 3. So one way to solve this problem is for when we're given how long they take to paint each wall, take each of these numbers, divide them into 1. So 1 divided by 2, 1 divided by 3, add them up, take this sum and divide it into the number of walls that they have to paint. And that gives you t. Because if you do it mathematically, you can see that we get this equation here. And then when you solve for t, you get t equals 5, which is the number of walls to paint, divided by this expression, which is just how long each of them takes to paint. It's that sum of the reciprocals. So that's one solution. That's Kanishk's solution to the problem. Is pretty smart. And once again, if you've done math counts, this is one of the problems that comes up frequently in different forms. So we'll take a look at the code, and Kanish can explain that. And then we'll briefly go over how binary search can be used to solve the problem. If you didn't see how to solve it mathematically, you can still use binary search to solve it. This was called wall painters. It's called painters. Here it is. Wait, solution 2.java. And you can see how short the code is. It's really nice. So Kanish, do you want to explain that?
It's not showing on the screen. Should I screen share or?
Oh wait, no, never mind. I forgot to. Just a second. Sorry. Yeah, here it is.
So in this code, the first few lines are just reading in the number of people, like how many painters there are, and the next number is how many walls there are. So we take a double total and we loop through every single rate of the painters, because on the second line, it shows how many hours it takes for each painter to paint one wall. And if we do 1 divided by that number, we can figure out how much time it takes each painter, or how many walls each painter will paint in 1 hour. So like this time, like Ishan was talking about t, we set the t as 1 to see how many walls each painter can paint in 1 hour. And we add all of those to total. So at the end of that, we have a total, which is how many walls, if all the painters are working together, can paint in 1 hour. So at the end, all we need to do is divide the number of walls by total, which is the rate at which, or how many walls they can paint in an hour. And we do printf. So printf is just limiting it to 3 decimal places, which is what the problem wanted. Yeah.
That's great. And then for the binary search solution, it's a little more verbose. Well, actually not that much. Most of it is just creating variables. But if you remember in the binary search, we have a lower bound, we have an upper bound. Over here, we're binary searching for the number of hours necessary. And the way that we do this is we have low starting at 0. We have high starting at this really large number. This is the worst case number of hours needed. And we also have an error over here. So this is something you haven't seen before. This is binary searching for doubles, because our answer can be followed by 3 decimal places. We don't want just an integer solution. We want to have a certain amount of error in our. We want to find an answer within a certain amount of error, because in the end we're going to be rounding it anyways. So we start by lowest less than equal to high. Mid is in the time that we're testing. So we want to test if this amount of time is enough to paint that number of walls. So then I have this walls painted function that takes mid and tells us how many walls can be painted at that time. And it does what Kanish kind of described. For each person, it takes the amount of time they take to paint one wall, divides that into the amount of time available, and then it basically returns us how many walls can be painted with this much time. We check if the number of walls that can be painted is within 0.000001 of what the problem is asking us, then that's a good enough answer. We're going to break and print out our answer. Otherwise, we're going to have to go ahead and keep on binary searching and limiting our range each time. So that's the binary search solution to wall painters. I think our last problem for today will be Skater. Big Addition will cover a concept that we'll go over in more detail next week. So yeah, for this last problem, we'll take a look at Skater. Actually, Skater is pretty verbose. I'm just going to go ahead and explain it. This is a pretty nice diagram over here. So pretty much you have these platforms that are floating in space, and you start over here at the beginning, all the way on the left. You're given the X and Y coordinates of the platform. So that's what these are, 3, 6, 9, 3. These are the coordinates. And you're also given their widths. So this one has a width of 3, this has a width of 5, this has a width of 2, and this has a width of 1. Your goal is to reach a certain X coordinate. So in this case, we want to reach an X coordinate of 16. That's denoted by this gold line over here. And the way that it works is you can skate along the platforms, but when there isn't a platform underneath you, you're going to fall diagonally. And for every 1 unit down you go, you're going to go 1 unit to the right. So that's what happens over here. The person's skating 3, 6, then they reach 6, 6, which is the end of that the platform. They fall down all the way to 9, 3. They ride on the platform, and then they fall down. They just barely touch this platform over here. Because if you calculate where they're going to land, this is coordinate 14, 3 over here, which means this is coordinate 13, 15, 2. So they touch the very tip of this platform, and then they touch the very tip of this platform, and they arrive at 16. So this is an example of where the skater did make it, and then you would have to print out made it, because the skater is able to go from the start all the way to the end. In this example over here, the skater does not make it to the end. An example of when, let's take a look at an example of when they would not make it. Okay. So that we just saw an example of when the skater would make it. Let's take a look at an example of when they would not make it. So let's say the skater starts here. I want him to get to this coordinate right over here, this X coordinate, whatever this is. And so he starts off over here. He goes, he falls down onto the platform. He goes, but the problem is, as he's falling, there isn't a platform underneath him. So he just kind of he just keeps on falling, and he never reaches this coordinate over here. And so if the skater is not able to reach a coordinate, then you have to print out fell at whatever coordinate he fell at. So he fell at this coordinate right over here. So that's how the problem works. And it may seem pretty daunting, but think about some initial steps that you may want to take when you're given this problem. What do you when we're given these platforms, they aren't given to us in sorted order. We may be given this platform first, then this platform, then this one, and then this one. What do you think is the first step we should do when we're reading our input into an array or whatever you want to use to store the platforms? Is this, like, logically as humans, do you think it's useful for us to solve do you think it's easy for us to solve the problem if we're given this platform, then this one, and then that one and that one? Or is it easier when we get them in order so that way we can see how the skater moves?
In order?
Yeah. So the first step when we're reading the input is to sort these platforms. And how do you think we should sort them?
First from left to right.
Yep, that's correct. So the first thing you want to do is sort them from left to right, because the skater starts on the left, he wants to go to the right. What if I have two platforms that have that same X coordinate? And let's say I have something like this. They have the same exact X coordinate. So now, how do I break this tie? If two platforms have the same X coordinate, how do you think I should break the tie? How should I decide which one comes first?
Put the higher one first.
Yep, the higher one should come first because the skater is not going to magically fall to a platform. In the problem, this is not possible. The skater can't fall to a platform. The first platform that the skater comes in contact with after falling is the one that they have to take. So in this case, we don't care if there's another platform underneath. We want the one at the top. So that's the first step to the problem. It's to sort the platforms by X coordinate and the leftmost X coordinate and then topmost Y coordinate. And once we have that, it's just a matter of simulating the process. I used a priority queue for this problem, though that's kind of excessive. I think you could have used an array or whatever you wanted, like an array list. You wouldn't have been able to use a set because the platforms may not necessarily be unique. I'll go ahead and screen share the code so you can understand how it works. And this is what we call a sweep line problem. So whenever you have some like line segments, some sort of geometry problem and there's sorting involved, that's what you typically call a sweep line problem. Because we want to process the platforms in order from left to right, not just any random order. So let's take a look at the code for that. Skate order. Here it is, skater. So this is why object-oriented programming is important. And if you guys are taking, just like how in video games, Madhu created a video games class, we're creating a platform class with a custom comparable. So the platform has an X coordinate, a Y coordinate, a width. And I just created this variable for the right edge for convenience because it's going to be coming up when we have to code the solution. The platform is going to be sorted by by X coordinate and then Y coordinate. I'm just checking if they're not equal first. And then here I'm reading in the input. Here, while the priority queue is not empty, and basically the priority queue stores stuff in order for, it just stores stuff. It's kind of like a set, but you can have duplicates. So it's like a set, you can have duplicates, and you can also remove stuff fairly quickly. So the way that this works is we're going to take the platform on the top of the priority queue. And because we've sorted the priority queue, the platform on the top of the priority queue is going to be the leftmost platform, which is where we start. So that's good. And then we're going to check if we can reach this platform from where we're currently at. Then we're going to set the rightmost variable to the right edge of this platform. And then we're going to update our Y coordinate. So the way that the can reach function works, this function basically tells us whether we can reach a platform from a given location. R is the right edge of the platform that we're currently on. Y is our Y coordinate. So for example, let's say there's a lot of red here, so I'm going to change the color. Let's say we're standing over here at the end of this first platform, and we want to determine whether it's possible to fall to this one. Because it may be possible that there isn't any platform over here. Maybe the next platform is over here. And in that case, it's not possible to land over here. So we want to check whether we can hit this coordinate. And basically what this function does is some basic math and Boolean statements to check whether we can reach a platform. If we can, then we go to that platform. Otherwise, we skip it. In the end, we just check if the rightmost coordinate we have reached is greater than the target, then we print made it. Otherwise, we print fell out. So I hope everybody gets an idea behind this problem to sort the platforms, and then you just kind of simulate going across the platforms, checking whether you can make it to a platform or not. And then in the end, you basically determine, have I made it past K? If I have, print made it, otherwise print you have none. And yeah, that's the solution for this skateboarder problem. All of the problems are available on HackerRank. We also have the editorials in the problem packet, so you guys can check that out. And these are really great problems. They cover a lot of content, as I said earlier. So definitely something to solve. And you can see that I think our first place team got 18 problems correct, so that's pretty great. And yeah, that's the end of today's meeting. Next week, we'll be going over the big addition problem and a concept called binary exponentiation, which has a fancy name, but it's pretty simple. So yeah, you guys are free to leave. If you have any questions about any of the other problems or any concepts, you guys can stay behind and ask them, but otherwise, bye.